All right, so we're going to take a look at 3.1 factors. So today we're going to start working with prime factorization of a number. So just kind of discussing about factor pairs. So if we read the sentence together, because 2 is a factor of 10 and 2 times 5 equals 10, 5 is also a factor of 10. The pair 2 and 5 is called a factor pair of 10. So remember, pair is talking about two items and there's something that are the factors of a number. So we're going to run through example 1 together here. So I really don't have a lot of room, so I'm probably going to have to do a little bit of work down here. So the brass section of a marching band has 30 members. The band director arranges the brass section in rows. Each row has the same number of members. How many possible arrangements are there? So for this, we're going to use factor pairs. So the question asked us for the possible arrangements. So just looking at 30, it's always good to start simple. So for 30, we can do 1 times 30. There could be one row of 30 or 30 rows of 1. Okay, so we're going to go along that same. So we're going to look at 30 equals 2 times 15. So this could be 2 rows of 15 or 15 rows of 2. We could do 30 equals 3 times 10. Same idea, writing out 30 equals 5 times 6. And then 30 equals 6 times 5. So if you notice, now look at what I'm doing. So I have 1 times 30, 2 times 15, 3 times 10, 5 times 6, and now I'm starting to repeat. 30 equals 6 times 5. So I'm going to go back. I'll just kind of jump over here. 30 equals 10 times 3. 30 equals 15 times 2. And 30 equals 30 times 1. Okay? So in total, we have, and I will highlight, 1, 2, 3, 4, 5, 6, 7, 8 possible arrangements. So it's always good to make an organized list of factor pairs. You can stop finding the pairs when the factors begin to repeat. So as you noticed, I found my original set of pairs, okay, and then my repeated ones, this is my main group here, but for my total possible arrangements, I knew, okay, well, I basically just have to double that. So this was 4. Well, 4 times 2 gave us that 8 possible arrangements because you can write them the other way. Okay, so right here, we're going to look at prime factorization. That was back up here. Sorry, I didn't have a lot of room, so we had to take that space. So right here. So prime factorization of a composite number is the number written as a product of its prime factor. You can use factor pairs and a factor tree to help find the prime factorization of a number. Okay? So what I want us to do is we're going to take a look at 60 as an example. Oh, that's why I had all this space. That's okay. We'll move over here. So let's look at 60. And we're going to work through prime factorization of this using a factor tree. So just think we're at the top of the tree, whereas if you have a Christmas tree, this would be where your star would be. So from here, let's just start with 2 times 30. 2 times 30. That's a pretty obvious one for breaking down 60. And we usually don't want to start with 1 times 60 because that's technically what this already is. This is 1 times 60. We want to break it up. So do the next largest factor. So 2 times 30. And then from there, we can continue on and break up 30 to be 2 times 15. We can keep going. We can break up 15 to be 3 times 5. Now, all that's left is 3 times 1 or 1 times 5. We can't break these up, right? That would not work for us. So once you get to a point where the only thing that you could factor out is 1 in itself, then you know that you're done, okay? So what I want us to do now is we're going to circle everything that was done being broken apart. So 2, 2, 3, and 5. So these numbers are very special, okay? So these are our composite numbers now. So we're going to take these and just double check. 2, so that's this one right here, times this 2, times 3, times 5. What does this equal? So 2 times 2 is 4. Then we have times 3 times 5. 4 times 3 is 12. Times 5. 12 times 5 gives us 60. Okay, so that's good. So this means that these are equivalent. So this was our prime factorization for breaking apart using a factor tree of 60. Now, something really special about this group is that you have 2 of the same numbers being multiplied. So we can actually simplify this. So 2 times 2 can be rewritten as 2 to the second power, and then we have times 3 times 5. This would be our, using our factor pairs. So this is our prime factorization, okay? So this is what we would finish off with, okay? All right, so let's jump back over here. With example 2, we're just gonna practice using prime factorization of 48. So we're gonna do 2 separate trees so that you guys can see that ultimately, well, we'll see what they do, okay? So starting with 48 over here, I'm gonna work with 2 times 24. So similar as we did with 60, just cutting it in half. 24 gets broken down to 2 times 12. And then we have 12 being broken down to 4 times 3. And 4 is broken down to 2 times 2. So everything is left to be composite. It's just 1 multiplied by itself. Nothing else can be broken out. So let's circle all those. And we can't forget about this 3 over here. Okay? So ultimately this would give us, we have 1, 2, 3, 4 2s. So you can write it out first and then times 3. But remember, since these are all the same, there's 4 of them, so 2 to the 4th power times 3. Okay? So I want to show you another one using 48 again, because it doesn't always have to be the same. There's multiple ways that this can work. So we don't have to start with 2 times 24. We could do 3 times 16. Okay, so we have 3's done. 16 can be broken down to 2 times 8. And 8 can become 2 times 4. And then we're left with 4 to be 2 times 2. So we go back, circle what we have. 3 times 2 times 2 times 2 times 2. So again, we have 1, 2, 3, 4 2's times 3. 3 times 2 to the 4th. That's the same thing that we got over there. So they're equivalent. So notice that when you begin with different factor pairs, the results are the same. So every composite number only has 1 prime factorization. All right. So we will jump down to example 3. This one, there's a key word that I want you guys to recognize, and that is a perfect square. Okay, so that should kind of bring a little bit back to your pre-algebra material. So perfect square, and we're looking for the greatest one, right? So largest. That is a factor of 1,575. Okay, so because 1,575 has so many factors, it's not efficient to list all of the factors and check for perfect squares. We want to use prime factorization of 1,575, and we want to find any perfect squares that are factors, okay? So remember, perfect squares are like 4, 9, 16, because we know 4 would give us 2 times 2, 9, 3 times 3, 16, 4 times 4. So the next one would then be to get 5 times 5 would get us 25, and the list goes on, okay? So what we're going to do is, and you could use a calculator for this part, and you could think about, okay, I'm going to check and see if 1,575 is divisible by any of these perfect squares that I've listed over here on the right, okay? So if you took a minute and you divide those out, and you want them to be large, you would see that 1,575, and you should also kind of recognize, because the last 2 numbers here are 75, it's a little shortcut, that this is divisible by 25. So this actually, the factor pair would be 25 times 63. It's okay if you don't know that offhand, just that's why we would check that. So then we can break apart 25 to be 5 times 5. 63 would break apart to be 7 times 9. Okay? So from here, 5 times 5 is done. There's nothing else we can get from that. 7, also done. Now 9, would then be 3 times 3. Now your 3's are done. Okay? Always double check that the numbers that you have circled, so 5 times 5 times 7 times 3 times 3, this has to equal 1,575, okay? Which it does. However, this is not our final answer, okay? We want to know the greatest perfect square that is a factor. So we just worked with some prime factorization. The prime factorization shows that this 1,575 has 3 factors other than 1 that are perfect squares. So we had 3 times 3, that got us 9. That was a factor. We had 5 times 5, that gave us 25. Okay, so then actually there's a nice little shortcut when you're dealing with perfect squares. 3 times 5 times 3 times 5 gives us 15 times 15, which is 225. And you can check that 225 or 1,575 divided by 225 does work, okay? So which one of these 3 we have here, 9, 25, and 225, are considered to be the largest? Well, that would be 225. Okay, so this is just doing this while you're using this prime factorization. I mean, this is also something that you can do a little bit of guess and check, but it's good to kind of get relationships with these numbers and check and see how they correspond together. Okay, so from here you have some practice problems covering this 3.1. Remember to sign up for your Google Meet or your Zoom this week with Mr. Pruitt. Thank you.